Thank you very much for the introduction, and thanks to the organizers for the very kind invitation. Indeed, what I will talk about is recent work that I did together with Piotr Chruściel that appeared on the arXiv this January. So this talk will be about a mass in general relativity with a negative cosmological constant in 2+1 dimensions. And perhaps in front of this crowd, I don't have to motivate why this is an interesting question to study, but I will try to give you a few motivations nevertheless. So one reason why you might be interested in studying this problem is if you're interested in ADS-CFT. So you might have an interest coming from the ADS-3-CFT2 correspondence, which is one of the best understood examples of the conjectural ADS-CFT correspondence. You might be interested in 2+1 dimensions because they're interesting solutions. So you might at first sight think, okay, 2+1 dimensional gravity is trivial, but indeed there are black hole solutions. And you might also have a mathematical interest because the mass in 2 dimensions behaves in a very interesting way. So what I will show in this talk, so this is just so you have a glimpse ahead what is to come, is I will show to you a gluing theorem for 2-dimensional vacuum initial data sets for general relativity with a negative cosmological constant. So what we will do is we will take 2 initial data sets and we will glue them together as the asymptotic boundary to obtain a new initial data set. And we will determine the mass of this glued initial data set. So what this gluing does, it realizes manifolds with any mass aspect function, and indeed it exhausts all time-symmetric Banados geometries near the conformal boundary at infinity. So this is what is to come. So what I will start with are the solutions of interest. So what are the solutions that we need to show our result? Then I will very briefly talk about initial data, because the rest of the talk will actually be on the level of the initial data set. Then I will introduce the notion of mass that we will use in the following. And then I will talk about gluings of solutions. So I will talk how to glue together initial data sets. So this is what will happen. And let's get started with solutions of interest. So the first thing that you realize when you study 2+1 dimension is that it is very peculiar because the Weil tensor vanishes in 2+1 dimensions. And what this implies is that for vacuum solutions to Einstein gravity, the Riemann tensor can be written in this form here. So all vacuum solutions to Einstein gravity at fixed cosmological constant are locally isometric. So what are some of these known vacuum solutions? So here I just focus on static solutions, and then what I will need is this 1-parameter family of vacuum solutions. This can in fact be generalized to a 2-parameter family of solutions if you consider also rotating solutions. And this family of metrics is parameterized by this parameter m. It was written down by Banados, Teitelbaum, and Manzanelli in 1992. Now, this metric here describes a black hole if you have m greater than 0. So this metric has the causal structure of a black hole, which back then was a big surprise because this is still locally ADS3. For m smaller than 0, you have 1 conical singularity, and for m being exactly -1, you become smooth, and you just have ADS3. And constant time source of ADS3 is hyperbolic space. So perhaps just as a reminder, the conformal compactification of hyperbolic space is just a disk. So these are the metrics that we will need. But now we will forget everything about spacetime, and we will just talk about initial data. So in particular, what we are interested in is vacuum initial data sets. So in particular, we want to consider initial data sets which satisfy the vacuum constraint equations that you see here. And what we will restrict ourselves to is the so-called time-symmetric case, where the extrinsic curvature tensor is vanishing, and then the then the vacuum constraints equation simply reduced to this equation here. So the Ricci scalar of our Riemannian metric G is given by 2 lambda, and if you set the ADS radius to 1, this is just minus n times n minus 1, where n is the spatial dimension. So for n equals 2, we have R of G is minus 2. So what we will talk about in the following are vacuum time-symmetric initial data sets, or equivalently constant negative scalar curvature manifolds. So this brings me to the next point. This was very brief. Let's talk about mass. And typically, the way you define mass is using space-time methods. So you consider a charge associated with an asymptotically timed-like Killing vector field. However, it's also possible to package this information in terms of initial data. And that's what we will do. So we will define the mass purely in terms of our initial data set. Now, what we want to do is we want to consider a class of metrics which approach a background metric at large distances. And in particular, let me give you a definition here. So a metric is called asymptotically locally hyperbolic if it asymptotes to a hyperbolic metric as one recedes to infinity. So more precisely, what we will consider are metrics which approach to this background here. So if you remember the family of metrics that we had before, so this was the background with m equals 0. So this we will choose as our background metric. And we will consider a class of asymptotically locally hyperbolic metrics, which looks as follows, where here mu ij is referred to as the mass aspect tensor and describes the leading order deviation of the metric from the background. Now, and here everything is to be understood in the frame. So here everything I've expressed it in terms of this frame here, and the error terms are to be understood in the frame. Now, if you calculate the Hamiltonian mass associated to this reads as follows. So what appears in the Hamiltonian mass is this precise combination of the mass aspect tensor. So for this class of metrics, this is our mass, and in this particular combination, I will refer to as mu as the so-called mass aspect function. So if we compute this for an example, so for instance, for computing this for the metrics that we had before, these metrics which were parametrized by m, the Hamiltonian mass simply reads m, perhaps unsurprisingly. So this is our mass. Now, if you start acting with asymptotic symmetries, and this was investigated a long time ago by Brown and Hainaut, these asymptotic symmetries will preserve the fall-off, and they will keep you in this class of metrics here, but this mass aspect function will change when you act with asymptotic symmetries, and it will change in this particular way, where here S is the Schwarzschild derivative. Now, there's something interesting. So this is work by Balogh, Ferrer, and Pala from 1997, is you can look at what are these mass aspect functions, and you can prove that there exist functions mu that cannot be mapped to a constant by an asymptotic symmetry. So this was the mass aspect function, and how does the mass relate? How does the mass look like that's related to this mass aspect function? It's simply the integral over this. And so what we find is that the Hamiltonian mass, after you've acted with an asymptotic symmetry, has no clear relation to the Hamiltonian mass before. It's not an invariant. The question is, can you obtain a geometric invariant? So can you obtain something which is geometric, something which is invariant once you act with asymptotic symmetries? Something which one can propose is that you do it via minimization. So you can take this functional here, which depends on f, where f was the diffeomorphism of the S1, and you can ask, if I take the infimum over, does the infimum over all these functions f here exist? And if mu is greater or equal to -1, then the infimum exists, and it follows from something which is known as the Schwarzschild inequality. Now, if mu equals m is greater or equal -1 is constant, then the infimum of mu is simply m, and it's attained on the identity map. However, if mu is smaller than 1, then this functional here is actually unbounded from below. So if you start acting with diffeomorphisms, you can make it arbitrarily negative. And this was already investigated by Klein-Barnich and Blažar-Oblak in 2014. So these are a bit the peculiarities of the mass, which brings me actually to the gluings of the solutions. Yeah. Uh-huh. So the reason why I'm focusing on R of G equals -2 is because these are the constraint equations, right? Yeah. So they will still be they will be constant. So any curvature invariant that you can consider, right, in 2 plus 1 would be constant, right, because of this property that the Weil tensor vanishes. So the Ricci scalar. So if you take Rij, and you contract it, right, this would be a constant. Okay. Uh-huh. Yeah. Very good. So this is something we will come later to. So this will so perhaps if I haven't answered your question after the talk, we can come back to it. Yeah. No. So this follows from the coadjoint orbits, right? Because this is precisely what so very good. So this, right, precisely. So if you act with the diffeomorphisms, right, you will move along the coadjoint orbit. Right. Uh-huh. Right. So I think that, so Witten was one of the people that studied it. So there are several sources, many places. So we in particular used the analysis that was done by Balogh, Farah, and Palla, which I also quote here. But this question has been studied for a long time by many people. Yeah. Right. There are these exceptional coadjoint orbits, right? Okay. Yeah. So this brings me to the gluings of the solutions. And typically, the question that you want to answer when you want to glue is you want to answer the question: can we take two initial data sets and glue them at their asymptotic boundary to get new and interesting solutions? So this is typically why you do gluing. How does this work in higher dimensions? So in higher dimensions, there are gluing theorems that are developed in literature. In particular, there's a gluing theorem by Isenberg, Lee, and Stavrov that tells you the following. Given two asymptotically locally hyperbolic manifolds in space dimension n greater equals 3 with constant scalar curvature or general relativistic vacuum initial data sets, one can construct a new one by making a connected sum at the conformal boundary. And this is basically shown here. So what you do is this is a picture from our conformally compactified manifold from the outside, and you do some kind of surgery to it so that you take your original manifold and you construct a new one by gluing it together with a second one. And here in particular, you see something which has toroidal conformal infinity, and this way you get genus 2 conformal infinity. So this construction can be localized near a point at the conformal boundary. So this construction by Isenberg, Lee, and Stavrov can be localized, and this was done by Piotr Chruściel and Erwin Delay in 2015. So the advantages in this case that you leave your initial data set completely untouched in very large region, and you only do something localized to it. Yeah. I think this might become more clear in the next slide, because then I show how it works. Different. Well, so here, right here, you different. I mean, you can construct whatever you want, right? I mean, in the sense that if you you can take all kinds of manifolds and glue them together. So there is a region where you know little about the metric, which I will show just in a second. But in most of the regions, you know everything about the metric. But I think perhaps it will become more clear in the next slide. I also have to say, sorry, I have a problem with my ear, so I have some trouble hearing you from the back. But next slide will hopefully answer your question. So applications of these gluing theorems are for one, the positive energy theorem for spherical boundary at infinity, which was also done work by Piotr and Erwan. And we also used these gluing theorems to show existence of solutions with no horizons, with negative mass, and with higher genus at infinity, which is this picture. And this was these manifolds were not known to exist with these properties. So how does the gluing work? So now hopefully I come to your question. So here, this is again toroidal conformal infinity, because that's what we considered in the other paper. And you look at your manifold from the outside. This is the conformally compactified manifold. You zoom in close to the boundary, you zoom in on the patch, and then you have these epsilon regions. And what you do is you deform your initial data set within a half-ball of radius epsilon, such that it is exactly hyperbolic, not just asymptotically locally hyperbolic, but exactly hyperbolic in that half-ball. Outside of the half-ball of 2 epsilon, you have some you have the initial data set from before, so you don't touch it. You have precisely what you had before, and inside this inside the radius of epsilon, so in between the two radius, so in between epsilon and 2 epsilon, you have some kind of interpolation happening. You have poor control of the metric. So what you do then after you've done the deformation is you cut out the red half ball, and then you do the same thing to another manifold, and then you glue across the boundary of this red half ball to get your new manifold. And this is basically shown here. This is how the gluing works. So this was n larger equals 3, but we wanted to talk about n equals 2. N is the spatial dimension. As you've seen just now, the key step of the gluing is that you deform the initial data set in these epsilon half balls, such that within a half ball of radius epsilon, the metric becomes manifestly hyperbolic. Now, when n equals 2, if you consider vacuum time-symmetric constraint equations, you are already locally isometric to hyperbolic space. So there's that's very easy, right? So the gluing is simple in n equals 2. However, the mass is not simple in n equals 2, and this will be what I will talk about now. So let's see how the gluing works for n equals 2. So how did we do it? So this is n equals 2, constant negative scalar curvature. And the idea is to use asymptotic changes of coordinates to render the metric manifestly hyperbolic in a half disk near the conformal boundary. So what we do is we start with an asymptotically locally hyperbolic metric with constant scalar curvature and mass aspect function mu of phi. So we take this initial data set, we pick a point P at the conformal boundary. So if this is the conformal boundary, I pick a point P here. I find a diffeomorphism of S1 such that mu equals -1 in an epsilon half ball around this point at the conformal boundary. Now, this is this corresponds to solving this third order ODE here. And solutions always exist in a small neighborhood of P. So I do this, and then I blow up this small neighborhood of P using boosts. So I blow this up using isometries of hyperbolic space. And then I cut and glue. So this is the picture that you should have in mind. So I have my original manifold. I deformed the initial data set. I used asymptotic changes of coordinates to make nu equals -1 precisely here. I did the same thing to my other manifold. So I call my first manifold m check, g check, my next manifold m hat, g hat. And then I cut off here, and I glue it together. And because of everything I've done, everything is smooth. So when I put this together, the metric extends smoothly across the gluing surface. Now, the question that we wanted to answer is now, what is the mass of the resulting manifold when you do this gluing? This leads me to the following theorem. So what we showed is that given two asymptotically locally hyperbolic manifolds in dimension n equals 2 with constant scalar curvature, we have the following. If the masses m hat and m check are positive, then the glued manifold has mass m, which is determined from this equation here, where omega check and omega hat are parameters which have to be bigger than 1, but are otherwise arbitrary that we have to introduce in the gluing. If the initial masses are negative, then the glued manifold has mass m, and it satisfies this equation here. Now, this result, so then we also have a mass formula, but it's not in the slides. So we exhausted all these cases, positive to negative, 0 to positive. There's a whole list of subsections. But I can show it to you. So if I glue two BTC black holes together, then I can also interpret, this is, so to speak, a mass addition formula, right? You give me two masses, I give you the mass of the glued thing. But I can also interpret the same thing here as an addition formula in terms of entropy, right? Because what I have is if I glue two BTC black holes, I have first a horizon of length 2 pi square root of m hat, a horizon of 2 pi square root of m check, and then I get a horizon of 2 pi square root m. Yes. Yeah. Yeah, I just glued the initial data. Yeah, so I glue at the boundary. So what I do is I pick this initially small neighborhood around epsilon, which I touch, but then I use these isometries to blow it up, right? And then I cut and glue. But of course, these original epsilon balls, they extend into the bulk, right? They are anchored at the conformal boundary, but they extend into the bulk of my manifold. Yeah.
Because your initial data is
yeah.
Well, the disk or a disk with handles.
Yeah.
Now you have another disk with handles. How do you glue together? Did you glue the two disks together and make a surface without boundary?
No, so perhaps I should draw. Thank you very much for the question. So what I do is I have this disk, and I have another disk. Then I have my epsilon neighborhood. I have my epsilon neighborhood. This epsilon neighborhood, I can blow it up, so be half of the manifold essentially. And then I cut this off, and I glue here. So all across this boundary. So this is an interpretation of can also be interpreted as an entropy addition formula if you wish. How do we get to this? So I showed you the theorem, but what is the idea of the proof? And the idea of the proof is to leverage this classification of Balog, Farah, and Pala. So we could have, so there are many papers that analyze coadjoint orbits of the Virasoro algebra, but we used that specific paper here. And in particular, what they use and what we use by using their results is that classifying coadjoint orbits is equivalent to classifying diff plus as one in equivalent solutions to the Hill equation. So how does this work for us? So what we do now is we consider the Hill equation, where here phi is an R and mu of phi is a 2-pi periodic function. This here is the Hill equation. And if we now consider changes phi goes to phi bar, where f of phi is a diffeomorphism, then the new function psi bar satisfies again a Hill equation. But now with mu bar, with a new mu bar that has precisely the transformation behavior that we want. So what you can get out of this is that you can get the classification of the functions mu up to this transformation mu goes to mu bar from invariants of the Hill equation. So what are these invariants? So invariants are the number of zeros of the solutions of the Hill equation, and also something which can be inferred from the so-called monodromy matrix. So if you have a basis of solutions, psi1, psi2, then periodicity of mu implies that also psi1 of 2 pi plus phi, psi2 of 2 pi plus phi is also a basis of solution. Hence there is a matrix M, which is called monodromy matrix, that is defined through this relation here. Now, if I do a change of basis, this matrix here will change. However, the eigenvalue type of M and its trace are invariants. And it's these invariants that we will use in our proof. So what we do is, when we do the gluing, we also do the gluing of the Hills equation. So we have our original manifold, we know what the associated Hills functions are, and then we infer the glued Hills functions by a calculation. And in particular, what we obtain, what one can calculate is that the new monodromy matrix, so the monodromy matrix after you've glued, is given by this particular formula, where M hat and M check are the monodromy matrices of the original manifolds. So if we calculate M hat and M check, what this gives to us is the mass of the glued manifold via the invariance of the Hill equation, as we just discussed. Yeah, we also were very confused about this minus M. We thought we had a calculational error, but yeah, there's we just get it. No, it's at least not for me. So. Well, I think so. Perhaps this is, but it doesn't quite give you the explanation, right? I mean, so what you can of course check is that you can do a consistency check. You can say, okay, I glue things together that I know what I will get out of, and then you get a consistency check, and indeed this works for us. But yeah.
You said that the solutions is two-dimensional. The basis of solutions.
Yeah, two. Mm-hmm.
You take the product.
Yeah.
Yes, so there are two times two.
Yeah, 2 times 2 matrices. Yeah. Yeah, so, right. So what we do is we calculate this new m, and then what we also need, we take the trace, and we also determine the number of zeros, and then we know in which case of the classification we are. So we just, yeah, you have this monodromy matrix, you calculate these associated things, and then you have everything. Yeah, so this brings me to a theorem. So what we showed is that all mass aspect functions can be realized by smooth asymptotically locally hyperbolic constant scalar curvature manifolds, which have at most 2 conical singularities. So how do we do this? We do it by exhaustion in some sense. So what we do is we glue constant mu equals m solutions, we calculate the monodromy, and then we exhaust all the cases of the classification by Balog, Ferrer, and Palla. So how does this connect with the literature? So there's a work which I know to go back to Banados from 1999, who showed that near the conformal boundary at infinity, all smoothly conformally compactifiable constant negative curvature metrics can be written in this form here. So this is this simply arises because the Pfefferman-Graham expansion stops in 2 dimensions. So what you get is that this is an exact solution of the Einstein equations, where f2 of phi is an arbitrary smooth function and is related to the mass aspect function in this simple manner. So it's just simply given by 2f2. Now we know that the mass aspect functions are classified, which is this work by Balog, Ferrer, and Palla, and also, of course, Witten and other people. And we also know that constant mu corresponds to a BTC black hole, to 1 conical singularity or hyperbolic space. Now, what we show is where can the other mass aspect functions be realized? And in particular, we show that they can be realized by smooth asymptotically locally hyperbolic constant scalar curvature manifolds which have at most 2 conical singularities. So to sum up, what we did is we developed the gluing theorem for time-symmetric vacuum initial data sets for GR with a negative cosmological constant, and we derived the mass formula for the glued manifolds, which gives us this theorem here. Thank you very much.